Okay. So this is probability theory. Okay. And feel free to stop me and ask questions anytime. Okay. And and, um, and yeah, you can ask questions in Sinhala. And unfortunately, I don't know Tamil. But yeah, ask questions in Sinhala, and I'll answer them in Sinhala. Okay. And you know, as you guys can probably can find appropriate lectures for this thing somewhere. But yeah, I'm teaching it and I know Sinhala, but you ask questions from Sinhala if you want. Okay. Now, okay. So let's and this is the textbook that I'm following. Okay, I'm following this textbook right here. First, look at rigorous probability theory by Rosenthal. And this is a very unique book. So we are following the textbook. By Rosenthal. Okay. And this is a very unique book because typically this material you learn it after you do measure theory. Okay. But this book just builds up the measure theory as needed, and then just directly uh, goes to probability theory. And uh, yeah, that's a huge thing. Okay. And then but yeah, now, and you want to think about this thing, think what I'm doing, think of this as a, don't think that this is a very advanced course. It is advanced course, but this is foundational. Okay, think this course as trigonometry for A levels. Right, so this is the first thing you learn in A-level mathematics, and you can't do anything without this. Okay. And this thing is like that um, for quantitative subjects. Okay. So so what you do, let me say something for the first years who has showed up. So you learn this one. Tarushi, that's not Tarushi. Okay. Uh, uh, so think about it this way. Okay. So there is a course you learn probability and stat, and this is uh, from Saratsa. And this is enough. This provides very solid foundation for a lot of stuff, right? And you can go work in data and this and that, and this is enough. Okay. And but if you wanna go a little bit further, I mean, for example, you can get the foundation to start doing actuarial exams with this. Okay, and for the first years, okay, for the first years, I want all of you to do actuarial exams from the first year. Okay, so get into that course, and I'll manage those things. Okay, you don't have to think that you don't have to think that you go to physical science and then there's no jobs. Okay, I want you to come to physical. If you're in physical science, I want you to get a job that uses what you learn in physical science. Okay, and they also, I mean, when I was teaching at Japura, in my fourth year, and there's this uh, kind of the best student, so like first, yeah, he was among the first four students, and and it turns out he's doing IT degree on the side. Okay, he's doing two degrees because which is a perfectly fine thing because everybody knows that if you do just the special degree, then you can't. I mean, you need something else to do get a job. Okay, so and this guy was doing IT degree on the side, and uh, but you can do actuarial exam instead. You do the stuff well. You learn you use what you learn in the campus, and then you kind of get a job that uses that knowledge. Okay, so uh, let me give you another WhatsApp link. Okay, uh, okay, here is a WhatsApp link, and you guys can join to this group too. Okay, let me share it in the chat. And this one has once you in here, I'll guide you to relevant courses. Okay, and actually I will set up something for actuarial mathematics. Okay. Okay, where was I want you guys to kind of get a job or like build a career with the stuff that you learn from the university. Okay. Now, that being said, this stuff is difficult. Okay. Now, what's coming now is difficult. Difficult. Now, so let's start here. So you have probability. So this is what you learn in A level. A levels. So you have a, sample space omega. It's called the sample space. Okay, and there are outcomes. These are outcomes. Okay, and you work with this picture, right? And for example, if you toss a die 2 times, okay, So this is the die, the first one, and this is the second die. It's the second one. So we have 1, 2, 3, up to 6, and then this one also has up to 6. So we have we take the product set to be the space of outcome. So this is like 3, 4, for example. Okay, so and these are 3, 4. And these are like individual outcomes, and then you have the sample space. Good. And I'll go a little bit slower, and because we have big audience, and let's keep them for a while, okay? And yeah, okay. So this is the setup, and then you have events, and you have events that are like having the sum of the dice to be equal to 5. So that's that event. So then you have, for that you have 1, 4, 2, 3, and 3, 2, and 4, 1. Right. So events are just subsets of these are events. Is a subset of, yeah. Right. And if you ask what are all the events, so have a set of events. What is the set of events? This is same as the power set of omega. Okay, so the power set notation is all the subsets of omega. Okay. Now, so this is the A-level setup, and then here is another example. So this is example 1. And then you have example 2. Example 2 is, let's say you have a you have the interval 0, 1, and let's say something is gonna show up in uniformly in here. So this is like uniform. So for example, if you look at the event,
No, mira, no ha ido.
so we have the set E. Let's say you can think of the event as this set 0 and half, right? And then you can assign the probabilities for this event. That will be half. Okay, so you have seen uniform distribution. Okay, good. And this is like another thing that we use in probability. Now, and you have the example 3. Example 3, let's call it an infinite coin toss. So this is interesting one. Okay. So you flip a coin infinitely many times. and it doesn't end. Okay. Now, in here, in this setup, so in this setup, outcomes. So this is the sample space. So these are just sequences. This is like can be like HHH, all the H's, and then can be HT, HHH, sorry, THH, and so on and so on. And then it's really wrong to write this thing as a list, okay? Because this set sample space is actually uncountable, meaning outcomes, okay? And then you have events like event E is first coin toss is head, okay? So I mean, we can talk about the probability of E. In this case, that's also going to be half. We are assuming the coin is fair. Okay. Now, the problem, so with these three examples, so now there is a big problem with this. Okay. If you ask the questions tiny bit carefully, so example one, example one, this one is fine. Okay, so we have so in this case, for example, you can take a set with a single outcome. A is let's say 1 5. Okay, so that's outcome. That this is also an event. Okay, and then you want to assign probabilities to events. Okay, and in this case, set of events are this. Okay, you have the power set of omega. Any subset of omega would work as a event, and then we have no problem assigning probabilities to those events. Okay. Now, if you go to this example, example 2, so in here, in example 2, it looks like what we have is omega is 0 1 interval. Okay, and you have probability that assigns values to these events, and then the events let me denote it by F. Set of events, use the letter F. Okay, and it looks like this F is power set of omega. Okay, and then we take any, not just like 0 half interval, but you take any subset of the 0 1 interval, and then you assign a probability. Okay, and it looks like, you know, it should be able to do this. Okay, and similarly with the example 3, example 3, it looks like you can take, so it looks like you can take this omega as the omega and set of events as the just the power set of omega, and then you assign probabilities. Okay, and the first issue is, see, it turns out you cannot do this, the example too. So you cannot properly define probabilities for all the subsets of omega. Okay, it turns out you have to kind of work with a smaller collection of subsets. Okay. So let me go through this. So now let's look closer into this example. Uh, so example 2. So we have omega to be 0, 1 interval, and you take f to be the power set of omega, right? And then we assign probabilities to any set, and then you have the value between 0 and 1. Okay, so this is like if E is an element in F, then we can talk about P of E, probability of E happening. Okay. So this is so the way to do it is you just have this function. Okay, and now and you want the for the uniform distribution, you want this uniform distribution to work for in a certain way for the intervals. Okay, so you want the property want probability of the interval AB to be take any interval AB like this. You want this thing to be B minus A. So this is the first condition for if you take any interval, if we take any interval, we want this to happen. Okay, and then the second condition, if you have if you say A and B pairwise disjoint, disjoint, meaning that A intersection B is empty. If this is the case, then you want a probability of A union B to be equal to probability of A plus the probability of B. Okay, and so and these are the things you assume in A levels. Okay, but But now we need something little bit more serious than this. It's called countable additivity. Countable additivity means if not just for two sets, if you have a sequence of sets A1, A2, A3, dot. These are subsets of omega in our set F, and pairwise disjoint. Then I want the probability of the union n equals 1 up to infinity of an to be equal to the sum. Okay, and so let me call this condition. So this condition is condition A, and this condition is condition B. Let's say condition 2, condition 1, and condition 1. So now the proposition theorem, not theorem. So this is let me call it a proposition. So this is the proposition 1.2.6, and this tells you there does not exist uh, exist probability function there does not exist p going from f into here that satisfies conditions 1 and 2. So there is one more condition. Okay, condition 1, 2, and 3. Okay, so the third condition is if you take set E and then you translate it, meaning you add, let's say, R to it. So you want this thing to be equal to P of E. So that's the third condition. Let me talk about this third condition a little bit. Okay, here. So we are in the interval 0, 1, right? And when you add things, but in your mind you want to really think of this as a kind of a circle, 0 and 1 here. You want to identify this point with this. Okay, and in the sense with respect to like if you take a set E here and then you shift it a little bit, so this is your E plus R, right? And if you take the same set and then you add a little bit, you shift every points to by R, and then you should have the same probability. Okay, so that it's uniform when you shift it, you're not changing the size of the set. Okay, so now what's happening? So let me define this plus R. So I mean, in the case when you have E here and then you add something bigger, then you get E to be in here, E plus R to be in this set. Okay. But if this happens, we want to kind of take this part and then you consider this part being inside here. Okay. Good. So it's like it works nicely if it was here. So this is your first set E. And then when you have E plus R, that lands in here. So this is like E plus R. Okay, so if you're rotating, going around a circle, then you don't have the issue of running out. Okay, so now, so let me define this plus x plus y is just x plus y uh, if uh, uh, x plus y is less than 1. And you say like x plus y minus 1 if x plus y is greater than 1. Okay, this solves this take care of that wrapping. Okay, going around the circle. Now, for if you have a set E subset in omega, and have some R, in, have R, let's say in 0, 1 interval. Then E plus R is the set of points x plus R such that x is in E. Okay, so this is the shift of the set E. Okay, now this third condition tells you that we want probability of E plus R to be equal to probability of E. Okay, now think about this thing, and this should kind of this should be a little scary, or like not scary, and because this is telling you that whatever you were doing in in high school or even in the university most of the time if you're not taking a measure theory course. So this setup fails. Okay. So when you do probability, you have a when you do probability, you have a outcomes, and then you have the sample space that you get out of the outcomes, and then you have events, and for the events, you take the space of events to be the power set of omega, and then you have a probability defined on all the events. So this setup breaks, okay, and and similarly, that setup breaks in here too, okay. So in here, you cannot do this, okay. So now let's see proof. Proof is actually really interesting. Um, and actually, uh, uh, the book's textbook tells you it is okay to skip this proof, okay, and it is complicated. You can skip it, but uh, yeah, we'll go through it now. Uh, Proof. So what I want to do is so you have a uh, proof idea. Uh, okay, so the uh, so we want to write. Uh, so I'm gonna break up the. So this is my sample space omega, and I'm gonna break this thing into a bunch of sets, okay? And actually a lot of sets, okay? And so the way I do it, this is done with the what you call I mean, we create what you call a partition, and the way you do partition is we work with the equivalent relation. Okay, so you consider this equivalent relation on omega. This is my interval 0, 1. We say x is related to y if x plus r equals to y for some r rational. Rational number in the 0, 1 interval. Okay, so if you take the if you take a point and then you add a rational number to it, you get y, and then you say that they are equivalent. Okay, so show that that relation is actually is an equivalent relation. Okay, and you can verify this easily because you can say you have to say that it's reflexive. X is related to X because you can take R equals 0, and if if X is related to Y, then you can say Y is related to X. Um, uh, so typically I want to say that if X plus R equals Y, then Y minus R equals X, but minus R is not in that set. But the role of the minus R is played by 1 minus R. Okay, so it's going this way. Going backwards can be done by going forward 1 minus R. Okay. And then the third thing is if X is related to Y and Y is related to C, then you want to show that X is related to C. So if you have X plus R1 equals Y and then Y plus R2 equals Z, you can take X plus R1 plus R2 equals, it's going to be equal to C. If R1 plus R2 is greater than 1, you can take R1 plus R2 minus 1. Okay, so this is easy to see, and once you have that, and these are the equivalent classes. So if you take the number, let's say half, and this and all the numbers that are equivalent to half, those are going to be in one equivalent class. Okay, and then you have this number root 202. This is irrational number, and then you have all of its friends. Okay, and then you have some giant set like this. Okay, now good. So we have x and omega. Now consider uh, consider set H. That's a subset of omega, such that uh, such that H contains exactly one element from each equivalent class. Okay, so let me draw this set H in here. So H is like this. So it goes through. So it is some set like this. Okay. Now there's something interesting happening. Okay. Now what happens if you look at this set? Let me draw it. So I am shifting this H. Yellow is not good. Blue. Now I'm shifting this h by some rational number, h plus, let's say 1/8. I'm shifting this h, okay? Now, I can do this thing for any rational numbers, okay? So we can write, verify this. This omega is a disjoint union of R in, let's say, 0, 1 interval, and R is rational, of H plus R. Okay? Uh, let's prove this thing. We have babies here. So, proof. So, all these H plus R, these guys are subsets of omega. Okay, so that means the union of these guys. It's going to be a subset of omega. Okay, and from for the other direction, so if you take some element x in omega, and then if you look at the equivalent class of x, and you take you consider the equivalent class of x, this is set of y such that y equals x plus r for some r rational q intersect 0, 1. Okay, and then by the claim, we know that let's take x delta to be h intersect with this guy, because each equivalent class contains a element like that. Okay, so actually this set is x delta. We know that h because you're picking exactly one element from each equivalent class, and that's that one, and then we have this. So that means there exists some r such that x delta equals x x such that there exists some r in here. So x is going to be equal to x delta plus r for some r in here. 0, 1 intersect q. Okay, so that means x is going to be in here. Okay, so that means if you start with any x in omega, and you can show that it's belong to one of these shifts. Okay, so what's really happened in here? So we start with the it's easy to see from the picture. So if you start the x here, this is your x you started with, and this is your x delta. Okay, if you start with x, then you can find x delta that belongs to h, and then you can notice that this actually x stays in this here, in here. So the x is in a h plus r. Okay, good. So that means we have the this equality. So we have omega equals the union r in 0, 1 intersect q of h plus r. Now the next thing is to show that r in 0, 1, let's not include 1, okay? And r rational. And next we need to show that we'll show that these things are this union is actually disjointed. Disjoint union I write like this is the disjoint union. So this can be done if you have an element x in h plus r1 intersection h plus r2, then we should run into trouble. Okay, so this is telling you that x equals let's say h1 plus r1, and also x equals h2 plus r2, and this shouldn't be possible. Okay, so because this would tell you so this would give you h1 equals h2 plus r. We can find r by playing this r1 and r2. Okay, so but this is not possible because this is telling you that h1 is in the class of h2. Okay, but we picked only exactly one element of exactly one element from each equivalent class. Okay, so this yeah, so this would give contradiction. Okay, you cannot have x like that. Now this is very, now we're done with the proposition. So what we have some picture like this. This is my omega, and then we write this omega in this way. We pick a set h, and then we have kind of shifts of this. Okay, so we constructed this. So we have omega equals zero, 1, rationals. So we kind of partitioned 0, 1 interval in this kind of went across. Okay. And so now by these conditions 1, 2, and 3, so we have 1 that is equal to P of omega. Okay. Because omega is the interval 0, 1, and then we want to assign probability 1 for that interval, because the length of the interval B minus A is equal to 1. So this is equal to the probability of the disjoint union of these events are in 0, 1 R of H plus R. Okay. And now by 3, third property tells you the second property tells you that we have a disjoint collection of events. We have a disjoint, then the probability of the union is the sum of the probabilities. So this is equal to sum okay. This is countable additivity. Okay. Now the third but now we know that whatever that number is, it's a shift of the probability of this set is the shift of H by R. So that means it's this number should be same as probability of H. Okay. Oh, also in this step, I use the fact that there's only countable many terms in here. Okay, because the rational numbers are countable. Okay, so we do countable additivity with like countable sets. Okay. Now, yeah. So now what is the value of? So we have this wonderful equation. 1 equals sum R in 0, 1. Now, what do we do with the with this equation? And this is this doesn't work because so the P of H, whatever the value you take 0. If it is 0, then the left hand side is 0, because you're adding the 0 countable many times. You get 0, but the right hand the right hand side is 0, but the left hand side is 1. Okay, and then the other option is P of H is not non-zero, then you get infinity. Okay, so this would give you a contradiction, and this finishes the proof of this proposition. Okay. Good. Any questions on this? Good. Okay, here is a tough problem. And how about example 3? Can you construct the same similar similar counterexample for the example 3? Infinite coin toss. So let me set this thing up. So this is fun. Uh, so what you want, so you so the what you really after is this condition. So you'd want the condition 1. Okay, condition 1, these are like the kind of the basic sets. Okay, so you take these basic sets to be in the coin. Let me go through this. I'll set this thing up, but I'll leave you to find the counterexample. So the setup is omega. So omega is uh, coin toss. These are like the sequences like this, and so you won't consider these guys. So we like sets of this format. So this is saying that this set E is defined by first coin toss is H. Okay, and we want the probability of those things to be kind of the 1 over 2 to the n. Okay, so for example, if you take the set event where the first coin is head and the fifth coin is tail and so on, but you have like finitely many coin tosses, and you fix that and then you create the event out of that, then you want the then you want the probability of that event to be 1 over 2 to the n. Okay, so those are like your basics in sets, like the intervals. Okay, so basic sets. So we have intervals, and you can find the analog for that. And the third one is the translation. So if you take a set E and then you translate it by some G, you want it to be equal to E. Uh, so what's happening in here, let's say the translations that you allow, you take a set, you take a set E, of outcomes, and then let's say you pick like a finitely many places, and then you change the value of all those finitely many places. For example, uh, if the set has in the third place, if it has the set value h, we change that to 10 in all the all the outcomes of the set. Then you get like a translated set. Okay, and you want that condition. And if you have these three conditions, show that there you can always find a set like H where you cannot assign the probabilities. Okay, so this is a good thing to do in Piazza. Okay, let's do this thing in Piazza. Piazza is a site that we use for discussions. So I'll post the problem and then you can discuss it in there. Oh, let me do something else to get into all that stuff, and especially this is good for the first years too. So the first year students, if you want to do pure math, and you can yeah. So I will guide you to the to a Piazza site, and for you guys, there are 3 courses that happening right now. You can learn how to write a proof, and there is a multivariable calculus course, and there is the third one is the statistics course by Professor Sarat Bannaga. So yeah, you can take those 3 courses in there for the first years. Okay, now so we are done with the you're done with the main part, like the kind of we are kind of, because of this proposition we are entering, we have to change what we thought of in um, in in high school. Okay, so we have to say, like, you want the uniform distribution and you want the infinite coin toss, but the probability cannot be defined for all the sets. Okay, so you have to restrict the number of restrict the collection of sets where the probabilities are defined. Okay, now okay, so so this is the definition, chapter 2. Probability triples. Okay, so we have a probability triple is omega, f, and p. Okay, so the first one is omega. This is the omega is a set, and we call this thing sample space. See, in mathematics, like so like when you write it this way, so what is omega? It's a set, and it matches with what you learned in high school, and you want to think of this set as the sample space, the outcomes. Okay, and we are okay, and then this f uh, F is a subset of omega uh, satisfying these conditions. So the first condition is we have empty set and the whole set is in F. Okay, and the second one is if E is in this collection, then E complement has to be here. Okay, and the third one, if A1, A2, A3 have a sequence of elements in here, then union belongs to F, also the intersection. Okay. Good. So the and this thing, a collection of subsets that satisfies these properties will call, in other words, F is a sigma algebra. Okay, it's a sigma algebra of subsets of omega. Right, and I'll tell a little bit more about this thing, but let me finish the definition. The third property, so this is what P is. P is a map from F into here called probability measure, or you simply call it probability, and this satisfies these properties. Let me write the first one so that P of E is between 1 and 0 for all E in a sigma algebra. It is already mentioned in here. It's in here too. Okay, but let me write it explicitly, because these are the things that you have seen already. Probability has to be between 0 and 1. Okay. And probability of the empty set has to be equal to 0, and the probability of the whole set has to be equal to 1. Okay, and the third property is countable additivity. So if A1, A2, these are elements in here, the pairwise disjoint, then the probability of the union this is same as the sum. Okay. It kind of looks like a it looks like a good news. Okay. Because let me go through these things again. So how this connects to the high school stuff. Okay. So we have omega, that's fine, and then you have this one. Okay. This is called the sigma algebra, and this is where again like these are events. So these guys are called events. A set of events. So sometimes when you read undergraduate books, they will not mention this thing, but they would have like two different words for the event space and the sample space. And like for your life, you cannot figure out, or you have this event space. Isn't that just the subsets of the sample space? Uh, uh, yes, the problem is sometimes you cannot uh, define probabilities for all those subsets. Okay, so we define probabilities for the events. Okay, so it's in here. If you are an event, that's when we define a probability. So this looks like the kind of the fix for the problem we had earlier. Okay, so but the good thing is this F has these properties. You have empty set, and the whole set is an event. That's good. And you have an event, and then the complement has to be event too. Okay, and the third property, if you have any sequence of events, then the union and the intersections are also events. So it looks like we can do whatever the operations we want inside this sigma algebra, inside these events. You can like, you create new events out of the old ones, and then you assign probabilities. And you have these formulas and everything. All that can be done because the sigma algebra allows you to carry out those operations. Okay. And the question is like, for the uniform random variables, uniform distribution we had earlier, what is this F? How do you find it? So it looks like we have a special collection of subsets of the 0-1 interval that satisfies these properties, and you can define a probability in a meaningful way. Okay, and these are the axioms for the probabilities. There again, like the key here is we are not defining, we are not assigning probabilities for all the subsets, but only for the subsets of only for the events, meaning the elements of the sigma algebra and so on. Okay. So, and again, like these are the properties you want from a probability. It has to be between 0 and 1. Empty set, probability of the empty set is 0. Probability of the whole set is 1, and satisfies this countable additivity. Okay. Now, any questions? Any questions? let me do simple couple of simple things from of the probability. Okay, and read the book carefully. Okay, I'm following the book, but I'm if I see something that's not very interesting, I'll skip it. But you read it. Okay. Now let me prove a bunch of things, some facts. This is just to convince you that these three axioms for probability is enough to kind of create all the rules you had in high school. Okay, because you remember like there were like a lot of properties and this and that. Okay, so let's say the first one. Uh, so you had this one. Okay, this is fun one. For A, we have element in the sigma algebra. Write it this way. Probability of A plus the probability of A complement is equal 1 for all A in for any event we have this property. Okay, so if you stop seeing the screen or something, just let me know. Okay, immediately, because that's gonna mess up the recording. Okay, sometimes I forget to click on the shared screen and that create problems. Okay, now how do you prove this thing? Can prove this thing this way. So so it looks like this is some property about the you're adding a bunch of probabilities, and this is the one we have in here, right? And but this one is about infinitely many sets. Okay, and but it's okay because we can always create infinite sequence of sets by adding empty sets. Okay, so consider this sequence. Consider this sequence A complement, and empty sets. Events in here. Okay. Because A is in our A is event, so A complement is event. Now we can consider this sequence. That's okay. So by property 3, we have a probability of union of these guys equal to sum of the probabilities of A. Okay. And but what is this union? Union is union of all these sets. That's A, union A complement, union whole bunch of empty sets. So this is omega. And so what you have is P of omega equals P of A plus P of A complement plus bunch of zeros. Okay, so what you have P of A. So from this you get P of A plus P of A complement is equal 1. So you can use these three properties to get the familiar stuff. For example, this is a good one too. So if you have let me write this thing down. If A1, A2 up to AN pairwise disjoint, PD means pairwise disjoint, then probability of the union K equals 1 up to N, AK is this one. Okay, so this is fine. Because you can use the empty sets. We have only n sets here, but you can add empty sets to the for an plus 1 and so on, and then you have that sequence, and then you apply the third property here. Okay, so the point is, like, if you have countable additivity, that means you have finite additivity. Okay, now let me prove this thing. Second example is the first example. Yeah. We call it example A. This is example B. This is saying if A is a subset of B and A, B are in here, then probability of A is less than or equal to probability of B. This also works because note that B is A union B minus A. So you have like two disjoint sets. And so these are pairwise disjoint. And so that means the probability of B equals probability of A plus probability of B minus A. But the probability of B minus A is positive. So that means this is greater than or equal to probability of A. Okay. Oh, here is a fun one. Yeah, inclusion exclusion formula. So for any A, B in here, you have probability of A union B equals probability of A plus probability of B minus the probability of A intersection B. But you can get this thing from the from these just these axioms. So let's see. Oof. Probability of A union B is, let's write A union B as a disjoint set. So this would be A union B minus C. So this is pairwise disjoint. Let me write this square union. So when I write the square union, that means I'm telling that this is union, but also it's disjoint. So this is probability of A plus the probability of B minus A. Now, also probability of B is equal to probability of we can write the set B as B minus A disjoint union A intersection B. And yeah, so this is equal to probability of B minus A plus probability of the intersection. Okay. Now you substitute this thing into here. So you get probability of A union B equals probability of A plus probability of B minus probability of A intersection B. Okay. And let me do the let me do this one too. So we have let A1, A2 be a sequence of sets in here, sequence of events. And I'm not assuming anything. And then the probability of the union, this thing AN, is bounded by this sum. Right, and the idea is like if they're disjoint, then these things are equal. But it looks like we have more parts. Right. So let's prove this thing. It's a picture, and we use this thing all the time. Okay, we use it all the time, and so we have A1, A2, A3, and so on. Let's call this thing A1, A2, A3, A4, A5, and so on. And these things are not a pairwise disjoint. Okay, so what you do, you create these sets. So you take B1 to be A1. Let's say B1. Okay. Now you look at A2. A2 brings in some extra parts, but we don't want the parts that's already included in the previous ones. So I take B2 to be A2 minus B1. We don't want the earlier ones. Okay, and then you take B3 to be A3 minus B1 union B2. Okay, and then similarly, you define Bn plus 1 is An plus 1 minus union k is from 1 up to n bk. Okay. And the claim is union of An is equal to union of Bn. Union n equals 1 up to infinity is same as this. Okay. And the point is like this BNs are pairwise disjoint. Proof. I'll leave this thing as exercise, okay? It should be fun, but write it. And now once we have this, then we can prove this thing. Now, probability of union n equals 1 up to infinity. This is same as the probability of union n equals 1 up to infinity of bn's. Right? So these bn's are pairwise disjoint. So that means we can write this thing as n equals 1 up to infinity of probability of bn. Okay, and this is bounded by n equals 1 up to infinity probability of a, because this bn is a subset of a. Okay, so that would give you your proof. Good. Now I'll stop here. So the in next class, okay, we'll go through 2.2. We'll actually probably uh, yeah, we want to finish 2.2 to 2.4, and there is the main theorem. Okay, so read the book. Okay, and read the book, and it's going to be difficult, but uh, this is the kind of the most difficult part, because you're doing something for the first time, and it's not going to get easy, but this is the first time you're doing something difficult, and everything else will be at the same difficulty level. Or I wouldn't say less, but okay. So it'll take some getting used to. And now, then this is the important thing. Okay, I will assign homework. Okay, and I will have the other side. The side for this course. Now, so join these things, and then I'll send you the links to join to these classes. Okay, and what else? So I can reach you guys from the I have the two WhatsApp groups, okay? But all the discussion is gonna go into Piazza. Piazza is very nice because we can talk about things in there, okay? And then the last thing, so let's start this thing immediately. Let's get going. Let's give me a second. Okay, this is good. I have 14 kids. Mhm. Yeah, 14 kids. This is good. Now, Let's get, let me show you something, okay? Uh, you guys can see this uh, book, right? Yes?
Yes, sir.
No?
We can say it.
Okay, okay, you guys can see it. Okay. So you can write down the name Understanding Machine Learning from Theory to Algorithms. And there are some video lectures too, but let's read this book, okay? And then let's get this thing done. Uh, so my plan is we'll go through the foundations. Uh, we'll, oh yeah. Oh, so there's only 7 chapters for the part 1. Okay, and now we put 2 students for each chapter, and then you ask them to read it, and yes, get this thing done, finish it. Because what you're gonna go into is if you're taking this class, you'll be you're not gonna be a you need to shoot for the not to be a machine learning engineer, but machine learning researcher. Okay, so this foundation is needed for that type of thing. And so this, for example, like you don't want to just do this thing and see like, oh, it works, but you want to be able to kind of quantify how it works and understand the theory behind it. Okay, and just have a look at it, but after a couple of classes of the probability class, then we'll organize we'll start this class too. Okay, like in a you can have a like another day, and then you'll all gather and like people ask questions and so on. Okay, so I think that's it for today, and I'll see you guys on Thursday, and I'll send the links to join Piazza sites, and yeah, it's gonna be a while before you get into the class. There's some bunch of forms you have to fill, but you'll get there. Okay, good.
Uh, so I've got a question.
Yes.
Are the first years supposed to join on Thursday, or
Yeah, yeah,
is that
yeah, yeah. No, I
okay?
mean so the point is, do you know Epsilon Delta?
No, not really.
Okay, so you can't follow this course. So, but I'll put you to I'll put you into the Saratsa's course. Okay,
Sure. Yeah.
and also there is a course for you. It's called Introduction to Proofs. Uh, and you guys, I led you to the. I'll send you a link, and then you guys can join the Piazza site, and there are courses for semester 0. Let me show you these things, okay? And this is where all the courses are. I'll give you a link, and then you can, sorry, then you can go into here. So yeah, here are the courses. So you have this one, semester 0 courses, and you are doing introduction to mathematical reasoning. And this is probably you do in Japura, like this is the first like proofs course. Okay? Yes?
Yes, sir. So is that taught in statistics or is it a maths
Yeah,
course?
this is math. This is math, yeah.
Okay,
I'm a math person, not a stat person.
right.
Okay. So the but this will give you, so if your first year you take these three, and then when you take these ones, you take linear algebra, analysis 1, and don't take geometry or introduction to number theory unless you want to uh, actually do math special. Okay, there is a nice introduction to number theory course going on. We'll start it, and this is a good one to do if you really like, if you want to do math special. Okay, and this is kind of the second part of the Sarat Panna Access course. Okay, and then you have semester 2, and where is the course here? This probability theory course is this one, probability theory 1. Okay, that's this course, and I was talking about this one just a minute ago, understanding machine learning from theory to algorithms. Okay, so
Okay.
let me send you the link. Okay, I'll send you the link, and then uh, let's see, Google Form. Yeah, you can fill this one. You can fill this one, and then also let me give you another link to. Um, it's in here. Yeah, so there is this guide on how to fill out that form. Okay. So if you read this, if you watch this thing, and it'll be very easy to fill this form.
Open my group ഒക്കെ ഡിസ്ക്രിപ്ഷൻ എവിടെയാണ്?
Hey, so yeah, yeah, join these things, and do these things. And for the senior people, if you want to help, I can add you to the to take care of the little ones. Okay, so yeah, but let this thing going, get this thing going. And if you haven't uh, filled out this form, then please do. Okay, there might be some of you haven't filled out this one. Just fill it, and then I'll add you to the Piazza site. This one. Okay. And then from there you can find. So I think I created the probability theory class here. There is the probability theory class. I haven't posted the homeworks and everything yet. Okay, and also I'll put this video in YouTube. Okay. Any other questions? 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 Okay, so if there's no questions, I will stop the recording. And let me see, I'll stop the recording first.